Okay, welcome everyone. Thanks for being here so late. So this buff kind of was organized to the last minute because I've been working on this instrument called the LinnStrument together with Roger Linn for about a year, and then I suddenly realized that actually everything we've been doing has been geared towards open source and built on open source hardware, and like, actually this is a perfect topic for Devoxx. So I sent an email to Stefan about a week and a half, 2 weeks ago, and he said, yeah, we still have a spot for the buff, so there we are. So this is the LinnStrument. Who has heard of this before, this instrument here? No one has seen it? Does anyone know Roger Linn? Yeah, he's kind of the guy that invented the MPC, which is like this music production box that all hip-hop artists kind of use with a 4x4 grid, and they've got these square pads that they tap on and they make like hip-hop sounds and stuff like that. So he invented that too. So that's Roger Linn, is the guy that kind of invented the instrument by itself. I'm here at Bevin. I work at Zero Turnaround in my day job. I'm product manager. I've done a whole bunch of stuff, been in open source for decades, I guess. And I'm a musician. I do a whole lot of music stuff. And I've been hacking on musical instruments for quite a while. So I worked on the software of an instrument that's called the Eigenharp. And so those are 3 models of that. I wrote the software together with some other people for the Eigenharp. So that was done. Then I moved on to another kind of musical application, which is called Gecko, that allows you to use gesture control with your hands in the air to kind of modulate sound in 3D with a Lead Motion controller. It's been used quite a lot now in live performances. And now I've moved on to LinnStrument, where I've written the firmware and the tools for making this whole thing work. So going from the hardware to something that actually makes sounds and that kind of has user interface that has blinky LEDs. Right? Everyone likes blinky LEDs. So what is a LinnStrument? The LinnStrument is, and that's kind of the catchphrase, revolutionary music performance controller with 3D note expression. Yeah, okay. So let me give a short demo. This is an improvised setup. You see it actually play on my lap. So what you have here is basically a grid of notes. This is totally dynamic. You can rearrange how these notes are laid out. Basically what it is, so the way it's set up here is the blue light is the tonic of the scale, and then basically move up. And it's isomorphic, so every movement that you do is the same elsewhere. So you can you learn one gesture and it works everywhere on the instrument. And why is it 3D note expression? So this sound doesn't do them all. Actually, I think I've actually not set up one of these. There's one of them that's not set up. So what you already will see is that as I hit a note, instead of just hitting in the middle and making one sound, I can hit and slide. Right? And I can do this independently for different touches. So I can do. Right? So that brings kind of traditional musical instruments performance, where you have all the expression capabilities under your fingers and not with wheels to the side or knobs on the front. Everything that you can do is right here, and you can control it. I can maybe switch to another sound here if the computer cooperates, because it wasn't earlier. Let's see if that works better. So here you've got another axis that actually, so I can change pitch like this. Like at the same time, if I move in that direction, I open a filter and I close it. So I can have and change that again independently for each touch. So that is the basic premise of the LinnStrument, right? To allow musical expression with electronic instruments in a way that wasn't possible before, because Usually people use a piano keyboard that are basically on-off switches. Some of them have a little bit of aftertouch, but they're kind of hard to find or very expensive. And then you've got a whole bunch of knobs around it which kind of detract from your actual expression with your fingers. So that's the premise of the LinnStrument. But we're all geeks here, we're at Devoxx, so LinnStrument has been geared towards hackers and open source people and people that want to make this their own. So let's dive right in. What is inside there? So if you pull this thing apart, that is what you will see. You will basically see this translucent sheet that lies on top of the circuit boards that is just slid inside the chassis, and then a front panel that's just a metal sheet that is screwed on top of it. That's basically it. Then if you pull it apart even further, you can see that the metal chassis is really nothing much. It basically holds everything in place and has some grounding there for the electrical signals. And then you've got the sensor board that is like the top area where the silicone sheet is put upon. That will actually sense the touches of your fingers. And you will see these contacts to the bottom and to the right and to the top. These are the contact points through where the current will flow and will allow you, when you touch your finger, to actually get that sensor information. And these contact points are also the things you will control in the software to go through the different cells and obtain the sensor information when you need it when you're coding. And so on the back of the sensor board, you will see that there is another board that is attached to it that is actually the LEDs that shine through. So in the middle of each sensor there's actually a little hole where it's a little bit less sensitive because there is a LED kind of coming through. And those are connected with a traditional short ribbon. And then you can see here to the side, so that is this side here, that you basically have some basic connections. You can recognize the Arduino Due's ARM chip there. You will see that it's the same on the actual picture of the Arduino Due that I'm showing in the later slide. And then there's one kind of custom element here, which is an Arduino MIDI shield that was created by some guys, I think it's in Portugal or Spain, I can't remember, that do basic, they transfer data from serial to USB and from USB back to serial so that you can use this USB connector to actually send MIDI information. So that is kind of the inside of the LinnStrument. And if you now compare it with the Arduino Due that is shipped, you can recognize the same ARM chip. The reason why the Arduino Due was picked, which is kind of, I think, I'm not sure it's still the most powerful Arduino that's out there, but it was at the time, is that it is a 32-bit processor that is quite fast. It's quite a bit of RAM also that you can work with. And so here summarized, you can see that it's using only a fraction of the digital pins that are available through the Arduino, so the pins 33 to 37, and it's doing quite a lot over the serial peripheral interface, so the SPI interface, and it's using the slave select mechanism in the Arduino Due to actually select different peripherals that will get or be sent serial information to based on what you need. So the Arduino Due, kind of summarized, it allows you to send 32-bit information in a single CPU clock, which is quite important for the resolution of this instrument. We want to preserve the actual sensor data when we're working with it. So it runs quite fast, it's got a bit of RAM to work with, you've got these digital I/O pins that allow us to connect to certain things, and then the SPI interface that basically connect with the boards. So has anyone done any Arduino programming here? Yes? But if I make any mistakes, do not correct me. No, correct me. I've never done any Arduino before, but I think it's actually quite a fun environment if you're interested in electronics and kind of the maker mindset, getting something going yourself as a programmer. So this is a very basic, completely functional Arduino program. So you've got two methods that kind of summarize everything that you do. That's actually the only thing that's happening. You've got a setup method that is loaded when your board starts up or when it reboots, and then a loop method that is constantly being looped over forever and ever at 100% of CPU power. So that, to me, as a Java programmer using general purpose CPUs, was really weird to think of, that it's actually always going full speed ahead, and it's your responsibility to keep everything going as quickly as possible in your code. And so this example basically configures the digital pin number 13, saying it is an output, I'm going to send information over there, and then to that pin is a LED connected, and in the loop, every second you basically flip it to high voltage or low voltage, which is on or off, and it will then turn the LED on or off. So you have like a blinking LED with 1 second intervals. That's what this program does. It's very simple. So what else do you need to know? It is a language based on C and C++. So if you've worked with any languages that are derivatives of that, you will feel right at home. The language reference is very concise, which I found quite nice. You don't have to go through hundreds of pages of manuals. It's all just on one page, and it is sufficient to do almost everything with. So it's kind of a nice change. They provide you with an Arduino IDE that you can just download and get started with. And then I kind of said the things about the setup and the loop functions also. So one thing to know about this loop function, so which will be called over and over again at 100% of CPU. So these are the things that I kind of learned when I was working on the firmware here, coming from general purpose CPU land. So it's kind of weird, but if one of your algorithms or operations is taking too long, it means that something else is not happening, which can have severe consequences. For example, if you start using floating point math and calculate for too long, it might take too long for the LEDs to be turned on in the loop cycle, because these LEDs are actually continuously blinking. You cannot see it, but it's happening very fast. If you just take too long in a calculation, the rest will not happen, and something that might otherwise seem continuous all of a sudden starts looking like it's not working right. So, but that's your fault. You don't have another thread. There's only one thread. So what do you have to do? You have to kind of start designing everything in a way that it can be subdivided, that you can have short snippets that execute and then you get out of there, working with state machines, working with algorithms that can be kind of hacked up in pieces or delegate responsibility throughout while the main loop is going. And then one very important part there is, if you're used to relying on the garbage collection, don't, because you cannot have any garbage. If you have dynamic memory allocation in such an embedded device, it will really grind everything to a halt. So you start thinking in fixed data structures, and you start thinking in how data and data organization and the algorithms about how you organize the data are going to solve your problems, and not like, let's throw 1 million objects at the problem and it will solve itself. You can't, right? So basic just overview. I don't know what the kind of technical level of everyone here is, but I think quite high. So I did include this here for people that are starting out. So this is the little program that you saw earlier. The Arduino editor is quite easy to use. Basically, you just open the program there, and then you select the board that you want to work with. In this case, it's the Arduino Due board when it's connected. You select which serial port that it has to communicate over, and then off you go. You compile and upload it, and it will be sent to whatever device is connected. So if it's the Arduino Due board itself, it's going to be that. If it's the LinnStrument, it's going to be the LinnStrument, and you'll be able to hack on it. But I personally don't like the Arduino IDE. So just if you want to get started with this, I basically use Sublime Text 3 that has a very nice plugin for Arduino integrations. It's called Touches.ino, and it looks to me like a regular text editor that has nice fonts and good syntax coloring and highlighting and all the things you can expect from a regular editor, because it's Sublime Text. So if you want to get serious with this, I kind of suggest that you look at this this approach, because it made me much more productive when working on the Arduino platform than their IDE, which needs a little bit of love. I don't know what your experience is with that. It's, so how do you?
Is it possible to debug?
Yes, I'll get there, but it's not the debugging that you think of.
Like no,
it's like slit your wrists and look what happens. Debug. No, yeah, it's kind of poor man's debugging. It's print the lens and stuff like that. Yeah. Well, you have to realize that as soon as you, because you're working with hardware, as soon as you set a breakpoint, everything stops and nothing works anymore. So For example, in this case, if I would set a breakpoint, I would have no sensor information anymore, no sound would be coming out, I would not get any information sent that is turned into sound, so all of a sudden there's nothing to debug anymore. So it's it's like the ultimate Heisen effect, right? As soon as you start observing or slowing down one part, nothing about your embedded device works anymore. Even when you start printing out the information, it easily gets very slow because it has to send everything out over the serial bus, and your whole device starts grinding to a halt because there's only one execution thread, and if something is taking up time, something else is not happening. So that's kind of the downside. The upside is that you have no threads. So it's kind of nice to be able to say, well, I know that if I do this and then that and then that, it's always going to be this and then that and then that, and there's nothing going to come in between, and that is just the way that's going to happen. It's quite nice to kind of step away from, well, doesn't it have to be atomic and maybe volatile, and which kind of lock do I have to put around it? No, you don't have to do that. So it's quite nice. So how do you access now the LinnStrument? So now we're going straight into LinnStrument territory. There are a bunch of high-level functions that we designed, which is probably what a lot of people are going to want to do, is stuff like this. Like when you have a scrolling message that goes from one side to the other, right? You want to kind of set the LEDs and do stuff with them, or blink your LEDs, and so we figured that is something that everyone wants to start messing around with. So we've got functions actually, to very easily mess around with your LEDs. You can just set them to different color, brightness, and the coordinate that there had to be, and then light it with a default color. So default color here is blue. And then clear a LED, so it's very easy to work with. But what goes on under the hood is this, and I'm going straight into that so that you actually see that it's not that difficult to work straight with hardware. So basically what you do is you're working with a serial peripheral interface, so the LED board is connected to the CPU through that. And you select the slave select pin 10, which says, okay, I'm going to switch to the LED board. You set up a mode basically in the beginning of the setup method, saying how kind of the data is going to be organized when it's being sent to that board. And then how fast does it have to run? In this case, it has to be 21 megahertz because that's kind of the optimal speed for these LEDs. And so we know that the Arduino runs at 84 megahertz, so we just divide it by 4, so that's this clock divider method. And that's the only setup you have to do for that. Now it's ready to actually work with that peripheral device that is doing the LEDs, right? You also say that it's an output, and then whenever you want to transfer data to it, you basically say, okay, I'm going to notify over digital pin 37 that you have to start receiving data, and then you transfer it over the serial peripheral interface. You transfer it as 4 bytes, and once it arrived, you stop the serial write to the digital write to that digital pin, and then the board has received that information and can use that to turn on the LEDs. So that's kind of the low-level interface to this, which is quite easy, I think. So similar for the sensors, the way that the sensors are being done is that you first select which sensor you want to work with. And that was also to me as never doing hardware, and still I don't really do any hardware, so I only understand part of that. But I didn't realize that was happening. But since you've got a board here that senses pressure, up and down, left and right movement on each cell, you basically have to, the way the sensor is constructed, you have to say where voltage has to be run through so that it can actually detect that when your finger touches that the voltage is going through, right? So it's up to you to say, okay, let's now switch where the voltage has to go. And then it has to take a while because electricity it has to take a while to flow, and before it kind of stabilizes due to the circuitry and whatnot and interference. And so you select the sensor cell, you say, okay, I want to read the X, Y, or Z properties of the board. And then if you use a high-level method, like for example read X, it's going to read the X value. You've got the same for read Y and read Z. These are specific to the LinnStrument, but if you now dig deeper, this is again the similar way of communicating like with the LEDs. As you see, you set it up, you say I'm going to use slave select pin 4 for the serial peripheral interface. Again, the clock is going to run at 21 megahertz, and you're just sending it the data that you need. And then afterwards, you're going to transfer it back. And the interesting part here, I think, I'm just going to skip over the first part because you already saw that, but it's that delay microsecond 7. So delay microsecond 7 is not a standard Arduino function, but let's pretend it is. So it delays, right? Why is that necessary? That's exactly what I was just explaining, is because the board, the sensor board, is switching currents around. You need to wait a little bit for these currents to stabilize. Otherwise, your readings from the sensors are not going to be correct. They might just, the current might just be arriving at the moment that you're touching, and then it's wrong, or it might not have been even connected to the other side. So that took some experimentation for each part, so the X, Y, and Z axis, to find the value that is right to wait for based on the layout of the board, because it really is how the lines are being drawn on the circuit board and how long it takes for the electricity to go from one side to the other. And so the rest is again similar. You just transfer data through the serial peripheral interface to say which sensor data you want to get back, and then you get it back and you pack it from 2 bytes into a 16 bit data structure, and then shift it down to 14 bits. That's basically what happens under the hood. And then the foot pedals are very easy if you want to connect those. They're just digital pins. You configure them, say, okay, pin 33 and 34 is just a pin that I want to read. It's an input pin that's called pull up, meaning it's just reverse, and high is off and low is on. And then you just read the state. So quite easy. We didn't really make any abstraction for that. And then we also provided, so the way you want to connect with the serial and MIDI connections and USB and DIN. So USB is this, DIN is that. If you haven't done any music, you probably have seen that in the 80s and not any more after that. But so these are MIDI DIN connections. So you might either send it over the MIDI DIN connections if you want MIDI out there, or over USB, and you also might want to send MIDI information over USB or serial if you want, for example, to do debugging. Then you'll have to kind of connect with a serial connection and get the data in and out from there. So that's again very easy. Just say, okay, these pins, I'm going to switch them around to different modes, and then the circuit board that's connected to it is going to behave correspondingly. So that's kind of all about the hardware stuff. Got any questions about this? I'm not sure I can answer, but I'll try.
I didn't understand the thing with the clock you used to...
The clock divider?
Yes. I don't know
this part said clock divider?
No, any of them. I think you showed some before, and I didn't know.
Well, so this method said clock divider, what it does? Is that the question?
Yes, maybe.
Yes, okay. So basically, so the CPU always runs at 84 megahertz, right? Mm-hmm. It always runs at full speed, right? But the board that's connected to it might not be able to work at that speed. Mm-hmm. So based on which peripherals you've got connected to your CPU, you might not want it to pull every clock cycle. You maybe only want it to pull slower, so that it sends less current, so that you can get less crosstalk, because your circuitry might be designed for lower speeds. Mm-hmm. And that's why you set this clock divider, so that your actual interaction with the peripheral interface is going to be slower than the maximum speed of the CPU. Okay? Other questions? Yes?
Does it pull its current from the USB port?
Yes, the current comes from USB, but you can also connect a power adapter here if you wouldn't have it.
Does it have a life if it's not connected to a computer?
It has life if it's connected to an iPad.
Oh, okay.
No, it needs power, and it's a controller, so it only sends MIDI information. It will not make any sounds on its own. Other questions?
Yes.
Yes, sir?
Is the current flowing when you put your finger on it, or is it flowing all the time?
It's flowing all the time, but it will only flow where you actually set the analog switches so that the sensor is activated through current. And this happens so fast that you don't notice it. So it switches around in microseconds for the different coordinates. And So as I hold my finger on here, it's actually going extremely fast, but you don't notice it. It's only going to read, when it arrives at that cell and my finger is on it, it's only going to read it when the current is there. But since it happens so fast, you're never going to notice it.
But when you put your finger on it, has it an effect on the current, or is it just that the current is needed for the sensor to know that your finger is on it?
It's a good question. I don't know. I'll ask. Does anyone know the answer? I think it basically it has an effect on the sensor, so the current will continue going through, but it will change. Actually, I think it probably has an effect on the current, and that's what translates into the sensor. But I'm not a hardware guy, so yeah, it's a good question. I'll ask Roger, he knows that. Yes, Kirkjan.
So you've got this instrument, and you've got an API to access it. So what have you, can you give some examples of what exactly you've done?
Yes, that's going to come later.
Okay.
I got a few examples.
I wanted to ask about the programming model you are now using. So
yes.
You need to really care for lots of things for updating.
I'll get there.
The lights,
yes, I've got a few examples. Yes, got a few examples of that. There's a lot to cover. Not sure I'm going to detail enough, but we can talk about it later if you want to. I can show you some code also. So for debugging, we've got the serial monitor, which is basically, so if you want to use it with a LinnStrument, you've got this one file, you just uncomment this line, say that you want to get all the debug definitions to be enabled, and then you put it in OS update modes, which basically switches this to be serial instead of MIDI. And then you've got the different, so you have to click on serial monitor, which is going to initiate a serial connection to the device from the actual IDE, so that it's going to start displaying the serial information that is coming in. And then it's up to you to select which debug level that you want, so, right? But this is actually a quite sophisticated interface because you can just switch through debug levels without having to recompile. So that's the way we kind of figured how to do this. It's
do you have any marks on the sensors that you know which are
well, we've got these are all kind of user functionalities, and it's like the column right next to the ones that everyone uses. That's the one for debugging. But it's only going to be active if you activate a debug mode here. Otherwise, that column is not going to be active. So and then it's going to display like this. So you're going to get in your serial monitor saying, okay, debug level has been activated. This is what's happening. I had a touch. These are the values, and so on. And so just as an example, so what you see here in the serial monitor, is this readable? Yeah. These are the three parts of the code that are responsible for that. So as I touched on column 17 here and the rows lower than 4, I'm going to just set a debug level and print that out as debug information. And then as a new touch goes on, I've got these debug macros there that will kind of send this information over the serial interface, and this is how you can debug. It's challenging, but it's interesting.
Does it really influence the sensors?
It influences the sensor because every time you send out the serial message, it's going to slow down the rest.
But eventually it goes through the USB cable to the Mac, to the computer.
Look for example. So this is debug level -1. Nothing is going on. Nothing is being sent, right? Now I'm going to put it on the highest debug level. So now it's sending serial data, and you can see that the lights are flickering because it's doing other work. It cannot update the lights as fast as it used to. So now there is a discrepancy in the update frequency of the lights due to the messages that are being sent. Because that takes time. It's just the time it takes to send it through serial. That's it.
I thought that this always sends all the messages. And
but so when you activate debug messages, it adds new messages. It kind of it sends these messages that are relevant to the debug level. It's just to show you that since you're doing more work, other work is not being done. So the LEDs are not updated in the same way, right? So, a quick overview of the files in the firmware. If you ever want to hack on the LinnStrument yourself, so these are kind of the main files for the moment. we've got the LinnStrument. So .ino is basically the file extension for Arduino files, which could just have been .c or .c++, but they decided that would be .ino. It's just C and C++ in there. So you've got the main LinnStrument firmware one, which is global data structures and that setup and main loop. It's quite long because it's kind of got all the initialization stuff in there, but that's what it boils down to. Then you've got display modes that basically shows you this part. It kind of handles the fact that it's showing numbers or that it's showing these different interfaces. So based on the global state machine of what you're in, it's gonna light different LEDs basically. So that's display modes. Then handles the touches. So it's driven by the main loop, so it's constantly being called, so that it's always updating that information. Like you were asking about, when is that happening? Well, it's just always happening. It's so fast that you don't realize that it's scanning through it. Just like old televisions where you had that beam going up and down, right? So you didn't see it because it went so fast. Then we've got our primitive real-time scheduler, which basically hijacks delay functions, which I said, okay, the delay function that you saw there, pretend that it's an Arduino one. Well, this is kind of one that we wrote. It's like a regular delay function, but it also, while it's waiting, it continues calling like this global functionality, like, okay, I have to wait for, let's say, 200 microseconds because the voltages have to stabilize, but in the meantime, I also want to update the LEDs because otherwise you're going to see it. Or if MIDI information has to be sent out, it has to be sent, otherwise like the music data is going to be uninterrupted. So there's a bunch of continuous tasks that, like in a poor man's scheduler, is kind of doing that, kind of hijacking the delay functions.
You have only one thread. How do you do it? Wait here, but do.
Well,
That's the way.
that's the wait. Doing is the wait. Yes.
But,
and if there's still time, it's going to really wait. So yes.
How do you do timing then? Is there some other clock where you can?
What kind of timing? Sorry.
But you want to wait for 7 microseconds.
Well, it's got its internal delay methods. So if we realize that it's done, so then we might do an actual delay there for a little while until we know that we actually have to refresh the global functionalities. But it doesn't matter because CPU is always running at 100%. So you can just loop there eternally and then break out of it when you know that actual time spent is the time that you wanted to wait. So you.
That was the question. How do you know the actual time you spent?
Because it's got a counter that is of current time since startup, both in milliseconds and in microseconds. Tricky one with microseconds is that it rolls over after 70 minutes, so you've got to be careful about handling that correctly. So it's fun, right? It's like, well, we discovered that by just letting the LinnStrument run, and then every time after an hour and 10 minutes, we didn't sit by it, but like every time after we went from lunch, like it stopped. Why is it crashing? And it was basically just the microsecond timer overflowing, and any of our comparisons were wrong. So, so then we've got another file for the settings. Basically, if you've got one file that does the display modes, then you've got another file that basically reacts upon your presses here to change settings, and then it's gonna change the way things are laid out or how the instrument behaves. And then one other file that is one level higher than the actual sensor data. It corresponds sensors to actual touches, so that it's a little bit higher layer for you to work with. It encapsulates it in an actual object. So, and then some lower level files. Some of these we've already seen, so the LEDs and the sensor ones actually contain almost exactly the code that I showed, how to handle the LEDs and the sensors and those higher level functions. There's more in there also, but it kind of boils down what it boils down to. Then you've got a file that is responsible for doing the calibration. So since this is such an expressive instrument, the actual manufacturing process influences the way the sensor is going to behave, and you get manufacturing tolerances that are accepted and acceptable within the industry that have an impact on the actual sensor data that is going to be sent, because I don't know, maybe that particular sensor line was 1 micromillimeter, a little bit more to the top, but it's acceptable. Like, I think tolerances are 10% or something like that, but don't quote me on it. But there is kind of a tolerance that is accepted, and that means that if you would not do any calibration, the midpoint of each cell is going to be different. The distance to travel is going to be different. It might even not be distributed evenly. So we've got a mode here where you can set it into calibration, and then you go over it, and it just measures, and then afterwards it's going to do the interpolation so that it knows what it wants to get at. We know how this is being laid out. We know what the sensors are giving us back when you touch it here. And when I go through it, I know that this is going to be the X data. And then afterwards we can interpolate and make sure that each information we can get back actually corresponds to a uniform distribution of values across the surface. So that's the calibration part. And then some test and debug functions, if you want to kind of report everything on the surface and see like this huge grid of values as you touch it. But it's like the debug stuff, it's going to influence what is going on. Like a lot of the difficult things, like for example, do I still have sound? No, actually, because I've turned on serial. The fact that it's going from cell to cell, and now you can hear a shift because I've got quantize on. But if I turn quantize off, so I'm gradually going from cell to cell, right? But these are actually distinct cells, so I need to know when I'm moving from each cell to the other. So the fact that I make this transition, if I'm printing out debug messages at that time, it's impossible to detect that a transition is being made because I don't get enough information to know that I'm doing a transition. So that's kind of these things. Yes, you can debug, but often the debug interaction is going to skew the data. Yes, sir?
How many columns do you have? One light is one cell? Or?
Yes, one light is one cell. There are 208 cells.
Okay, you don't have separate. You don't have more real cells than the ones you see.
No,
okay.
No. It's like one-to-one mapping with the lights.
Okay.
Yes. Then we've got some auxiliary features. So we've got an arpeggiator here. So basically, it's going to arpeggiate over what I'm playing. I've got some faders that I can set up. So if I set some faders here, I can use this as if I would have long faders. So these are kind of additional functionality that we don't consider core functionality, or the fonts that you saw scrolling. A low row that you can use to kind of strum over. These things are in these files. So too much time doing it. Almost done. And then a few header files that you can use that are quite interesting. So a circulator, spelling corrector, circular byte buffer with independent push and pop locations, which is quite interesting for queuing. Then a channel bucket, I'm going to explain that later. And these debug and BDH, they're quite trivial stuff. Well, let's quickly go over this. When you program the LinnStrument, you've got these global variables. Global variables! But it's super handy. So you've got these are always available because you always use them. You know where it's actually currently at this particular microsecond positioned for the sensor, so which column and row it's going to be. And if you've got split mode on, so we support a way to kind of split the surface into two sections, so you can change that split point. But so to know where you are at, because you use that in most of the features, saying, okay, where am I? This is basic where am I functionality. You use that so much that it's global variables. Also, which mode am I displaying? It's kind of important to be able to access that directly, so they're in global variables. And then there's kind of global functions. Apart from the where am I location, also what is happening where I am, that's like the touch info, so you can get that from these functions. Which was my latest press, if you've got multiple presses going on, knowing that is something you use all the time. Also, that's like the focus one. And that's it. So now we're getting into what you were asking about, some specific examples inside the existing firmware. And I already touched on this, so per finger touch tracking, this thing, right? The Java developer in me would, well, I actually had a prototype doing that, would abstract out a touch session. So that starts, and then each touch session has a unique kind of identifier, and then I correlate these, and it doesn't work out. Too much memory churn, too much bookkeeping. And then we kind of realized that we actually have state that is right there, because we don't support 2 fingers on each cell. It's going to be hard anyway. You have to have very tiny fingers, but so normally you only have 1 finger touching each cell. So as you move from one cell to the other, instead of like abstracting that in a super level of information, we can just transfer the data and pretend that this cell actually becomes that cell and swap out the data and just continue tracking by kind of exchanging data. And since there's only 1 thread, you don't have to worry about thread safety. You just set the values to the other data structure, and that's it, right? You don't have to coordinate that. So that is how that goes. That is kind of the state to do that. So as there is a new touch coming on, what is it going to do? It's going to check if the column to the left, and this is all identical to the column to the right, and is all identical to the column to the left, if it's a candidate for a slide. And if it's a candidate for a slide, then it's going to verify if all the conditions for a slide are being met. And if it's that is the case, then it's going to do that transfer, and it's going to use that to update the actual logic that is going on. And otherwise, it's going to mark that cell as, oh, well, it was a potential slide transfer cell, but I'm not far enough in the transfer yet so that you can consider this slide to be a correct slide from one cell to the other. And so how does that translate into the actual code? You've got this whole bunch of conditions at the top. It's quite ugly, but it's kind of the only way to do it. When these things are not happening, so when you're not like, for example, if it's not a low row, then I don't have to do that. If it's not strumming, then I don't have to do slides and stuff like that. So all these things, it cannot be a slide transfer candidate if these things are happening. And then there are 3 other conditions. It's obviously it has to be touched, otherwise it cannot be a slide transfer candidate. Also, it could be in a pending release state. The previous one could be in a pending release state, and then the next one is, am I close enough? So when I'm doing the slide transfer, and when I'm on the edge, am I close enough to the other one for it to be a potential slide candidate? And this is where, if you start printing out debug candidates, you're going to miss that information because it might not be updating the X position correctly, and then you're not getting that fast enough. And so now it is a potential candidate for a slide transfer, and then what is the condition for a slide transfer? Basically, so the pending release count, I'm not going to detail this a bit because that's kind of a whole bunch of other bookkeeping. But the basic condition is, when I press harder on the sibling cell, then it's actually going to transfer that data. Because when you slide, initially your pressure is going to be on the first cell, and as you've migrated to the second cell, your pressure is going to be harder. And you're still pressing on both at the same time, and then I swap out the data. And so it doesn't require that whole bookkeeping of independent sessions. You just pretend that it becomes the other cell. By remembering the initial touch information, because that's important so that you can measure the distance traveled, right? And so that's what's happening here. It's very stupid just setting values from one to the other. And resetting the previous cell as if nothing happened. So that's basically it. So other example here is finding the right MIDI channels. So I don't know if anyone has experience with MIDI here. Who is like who's using? You use MIDI? Someone else uses MIDI? So you might know that MIDI on each MIDI port has 16 channels only to work with, which were designed to connect 16 MIDI devices. And so the way that more and more people are using it now is each finger is a device. So you can have 16 fingers, but 10 is usually enough. And so you've got channels here, so this is going to be one device, this is going to be another device, and I'm going to send that on another channel. Now the challenge is going to be, as you have multiple fingers going on, which channel do I pick? Again, you could say, okay, well, I know my logic. My logic is that I want to avoid reusing existing channel. I only want to use a release channel as late as possible so that the release trails from the previous ones can go on as long as possible. There's a bunch of other heuristics that I kind of forgot at the moment, but there's like this whole logical thing that you could evaluate for all the touches, but that again takes a lot of time. So the way to solve it was to write a data structure that has this information inherently baked into it. And the way the data structure works is like a bucket of water, and each channel, you know how many channels you want. Let's say that people configure it to have 10 channels. Then they're all floating into that bucket, and so they all have a different weight. And the one that's at top, you can pick it. And then when you pick it, it sinks to the bottom. And this means that that first thing is kind of solved, but at the same time, channels that are in use, they will kind of glue to the bottom. And they can start bubbling up again once they're released. So this kind of whole depth perspective inside data structure allows each step of the actual playing action to rearrange the data structures in fine-grained manners. So this kind of divides tactic to write your code in fine-grained manners is going to rearrange the data structure so that it's always correct, and that whenever you need a new channel, you just have to pick it. You don't have to start doing all this bookkeeping to find out what the correct channel is. And that is all inside that channel bucket header file. Another example is low row functionalities. Let me see if I can demo this, what a low row is. So I've got a strum here, but I might maybe change to another sound for you to hear that. Better with a guitar. So let's go back to that. So what is low row is basically when I can strum over the bottom here to do as if I would be strumming strings on the guitar, right? So let's see. Okay, so the way you might kind of in the traditional general CPU way of thinking implement that is, okay, I detect press on the low row. Let's now see which other presses are going on. I'm going to iterate through all the presses and see if they're corresponding. It's not going to work again in an embedded environment because you don't have time for that. So the way that is implemented is that whenever a low row hit is going on, it's just going to mark this particular state is entered in a state machine. And then it's going to piggyback off the scanning of the other cells, and each cell is always going to query, what's the low row state of? What's the low row state at this point in time? And if the low row state applies to it, then it's going to play another note. So what happens if so the first press that I do here is going to play a note, but if I then do this, actually, when I press, it's only going to record I pressed on the low row. But then when the scan arrives at this cell where I'm also holding my finger, it knows that I pressed the low row on that column, and the actual code that is at that cell is going to send the note, not the fact that I pressed on the low row. The fact that it's going on so fast, you don't notice that is happening. So the way that it's implemented is quite easy. Basically, when the sensor data is being updated, it's going to handle the low row state for that particular cell. If it was a new touch, it's going to also record the start of the low row, and if the touch is released, it's going to record the stop of the low row, and how is that then being handled? So based on each low row state, for example here the strum, if it's a strum, it's going to remember which column, so the sensor column in the low row state, which column was pressed. And then when the low row is being released, it's going to record that this sensor column was released. And then whenever you handle the low row state, it's just going to differentiate between if it's a low row cell, because there's other functionality in the low row here. For example, it could be a bend. I might be bending there. So it can be a bend. If it's a strum, then it's going to do what I just said. It's going to check for that column, and if that column is active here, is pressed of the sensor that I pressed at, then it's going to sound a note. That's all. And then the last use case of the actual firmware is sending MIDI. It was kind of staggering because we had these LEDs displaying, but as soon as we were sending MIDI, everything was flickering. Quite similar to what I showed there is this thing, right? Quite similar to that. Whenever it was sending MIDI, which is also going out over the serial peripheral interface, it was doing this thing. And why was that doing that? It's because actually the Arduino UART classes have a synchronous wait in them. So they wait until the device is ready to send, and then only it's going to proceed. So we had to patch the Arduino classes to, instead of having it loop and wait, just return, so that we could at that point say, okay, we're going to back out, we're not going to do anything, but we're going to continue doing our other processing, refreshing the lights, and we'll get back to it in the next cycle, and if you're then ready to send the MIDI information, send it at that time. So that was only possible by patching the Arduino classes, which is kind of nice, since it's open source, right? I really like the fact that I was able to kind of go in there and say, okay, we can't fix it, but thanks to the fact that the source code was available for the underlying libraries, we could actually take one step further and fix it. And then we could, again, divide and conquer. Instead of sending out the MIDI messages each time they happened, we just put them in a circular queue, and then instead of sending each MIDI message as a bunch of bytes, we only sent one byte at a time, but very fast, like iterating over it together with all the rest, and then made all the flicker go away. So these are kind of a few examples of concrete use cases inside the firmware. And that's it. I don't know if there are any other questions. Yes, sir?
How difficult is it to learn to play it?
To learn to play this? You want to go have a try?
No.
I find it quite easy because it uses very familiar gestures that most people that are already musician or have tried to play, they kind of press down. It's isomorphic, so you don't have to learn it a lot. Once you know one pattern, it works everywhere. And you can turn off features if you don't want to use any of the slides. If you just want to press notes, then you can just press notes. I don't know why it's. So now it's not making any slides anymore, right? So it's just individual notes. And you don't have to worry about the expression. If you turn the expression on, then you can learn kind of gradually each expressive part of the LinnStrument as it applies to you. Some other questions?
Was hexagonal layout considered?
Yes, it was one of the considerations, but then we didn't do it. Because this is kind of, if you kind of skew it, it kind of turns into hexagon layout. We might still do one version later. It's a possibility that whether the first iteration, too many people are used to the grid layout, and we want to see if the instrument is going to have the adoption that we hope it's going to have. And then we're thinking of doing other models that are laid out differently. So yeah. Yes, sir?
Can it simulate any instrument MIDI to just?
Well, so the question is, can it simulate any instrument? Yes and no. It can make any sound that that synthesizers can make, because it sends out MIDI information. But the biggest challenge is to create a sound that feels natural when you've got this sensor underneath your fingers. So yes, you can theoretically make it sound like anything, but it's probably not going to sound like many other instruments because you don't have a resonating chamber, or because you don't have any harmonics that play into each other, just to the physical nature of things. So it depends on how far you want to simulate. But it's just my personal view on this. I started, because this is kind of a nice use case, it's a guitar, it sounds like a guitar, but I don't care about that because I play the guitar. I'll just take the guitar, it sounds much better.
So who's going to use it?
Well, for the sound that I showed before, for example, a sound that never existed, sounds that you just created and that you can totally make your own.
Mostly sound engineer going to use it?
No, there's a lot of musicians that play the synthesizer that currently only have piano keyboards to play with, or switches that also are arranged in a grid. There are a few instruments already, like the Ableton Push, that allow you to do a little bit of expression, and the Keith McMillan Cuneo, but they're not that nice to play. They don't do it in as a precise manner either. So yeah. Other questions?
How much does it cost?
This one costs $1,500. There's going to be a smaller version that's cheaper also. But, yes?
What's open source and everything?
The hardware design is not open source, but all the software is.
Okay.
So, all the software, also the firmware updater, which is kind of, I should kind of write a post about that, because I was surprised about this. When you build something with your Arduino, you kind of expect that someone that ships a product with it will do firmware updates whenever customers need new functionalities. But there is no easy way to provide like a packaged updater so that customers just press update and it updates the instrument or the device that you created. The only real way to do it is like, okay, you have to download the Arduino IDE and then you open the source code and you compile it and you upload it. It's not possible. So we also wrote an open source updater that works both on Windows and on Mac, and you just plug in your Arduino device. It's gonna identify what your manufacturer ID is gonna be, so you don't even have to select the serial port anymore. As for the customer, you just say, okay, I detected your device, update, and it's just updating it. Like what you would expect, but apparently there's, because I searched for about 3 weeks for a project that did that, and there are like hacked tools that kind of do a little bit of it, but it's not really intuitive to use. So I think that is probably going to be interesting to quite a few people also to kind of customize that for their own projects. Okay, thanks a lot. Oh yeah, I'm gonna be around for the next conference in the Hacker Garden. So I have 2 of these with me. If you want to hack on it, if you want to play with it, if you want to try it out, I'll be there until Thursday morning. So
That was exactly the final question.
yeah.